Okay, guys, we're gonna start with this. Thank you very much for coming to this session of QPaper. Today's presenter is Álvaro Bermejillo. He's from la Universidad del País Vasco, Spain. His main interest is solid-state physics, especially magnetic materials. And one of his long-term goals is to become a professor. And today is presenting a paper about spin wave, which the main author is Kahiwara, who at the time the paper was published, that was 2010. He was part of the Institute for Material Research in Japan and the Materials Physics Research Group in Keio University. The lead investigator was Eiji Saito, who right now is leading the Saito Lab, which is one of the best labs in quantum nanoscience in the world. So that's it, a little bit of background. Now I give the word to Álvaro and continue the presentation.
Thank you so much. So let's start with the presentation. It's going to be on this paper that is transmission of electrical signals by spin wave interconversion in a magnetic insulator. So first, a bit of context. This is going to be based in spintronics. Okay, so before spintronics, what we have is normal electronics. So we start with very old computers and very bad-looking transistors that have to be made one by one by hand. And we've been developing these semiconductor technologies further. We've developed field effect transistors. We've developed CMOS technologies. And now we are able of putting 57,000 million transistors in a single microchip. But that is not enough. We want more. We want cheaper technology. We want faster technology. We want more powerful technology. So the problem is that semiconductor technologies cannot evolve forever. We come to a limit where we cannot make transistors any smaller because quantum mechanical effects start arising, and then our transistors stop being deterministic, and then we cannot use them for a normal classical computer. There is also another limit that has to do with heat dissipation. So these devices work with electrical currents, and due to Joule effect, they dissipate heat. And so we cannot use them with the frequency we want to, because if we don't let the device cool a bit in between signal and signal, they melt. And so the approach of this paper is going to give us a solution for that heat dissipation problem. What they propose is changing our transmission of the signal via a charge current and do that through a spin wave, which is a spin current. And the experimental setup is going to look like this. We're going to have a device, and it's going to have as an input a voltage, and as an output another voltage. But the thing that is going to carry the signal through the device is going to be a spin wave. And in order to understand what happens in this device, I'm going to give you some ingredients. The first, we're going to talk about magnetic materials. Then we're going to talk about spin interactions. Then we're going to learn a bit how spin waves work. Then spin currents, conduction spin currents, and the spin Hall effect. And finally, we're going to see what happens in the interface between two different materials, like normal metallic, non-magnetic materials, and a magnetic insulator. And that's two effects there. They are called spin transfer torque and spin pumping, and those will allow to charge from a current to a spin wave and vice versa. So let's start with magnetic materials. In order to have a spin wave, we need a magnetic material. That is a material that has some unpaired electrons, which we can excite and make precess so that we can have a signal go through the material. The ferromagnetic materials have macroscopic magnetization that we can measure very easily because they have aligned unpaired electrons that align due to two kinds of interactions, which are called exchange interaction and dipole-dipole interaction. We're not going to be so interested about this, but there is a very similar material that is antiferromagnets. It's very similar in structure,
But here we have that some magnetic dipoles cancel with other magnetic dipoles. So from a macroscopic point of view, we don't see any magnetization, but it has microscopically a magnetic structure. And there's a very special type inside this family of materials, which are called antiferromagnetic insulators, which have on top of their magnetic structure the property that they don't transmit electrical current. So that's going to be interesting because we will not want electrons flowing around and messing our sample to have a spin wave, because that would give us a damping coefficient that is going to make our spin wave dissipate and not travel through our sample. In particular, the material we are going to talk about is called jig. It's made of yttrium, iron, and oxygen, and it looks like this. It's a garnet, and as you can see, it has quite complex structure, and it's always like this with these magnetic materials. But yeah, that's what we have to work with. So let's talk a bit about how spins interact. So we saw a bit about that in last week's presentation with Danny. So the first thing that comes to your mind normally when you think about two spins interacting with each other is that each of these magnetic moments generates a magnetic field. And so these magnetic fields interact with the magnetic moment, and there is a torque, there is an interaction. If we make a quick calculation of the order of magnitude of this interaction, we set two electrons 2 angstrom apart from each other, for example, and they have the magnetic moment of an electron. And we see that that interaction has a strength of 10 to the minus 4 electron volts, which is not very high. So if we found another kind of interaction that makes spins talk to each other, then that would predominate over the other. And it is very mad that the origin of this interaction is not going to be magnetic at all. It's going to be pure electrostatic interaction. And the pure electrostatic interaction is going to make spins talk to each other. And how does this work? Well, we have to take into account that we have electrons, which are fermions, and so they are identical particles, and we have to anti-symmetrize their wave function. We have two ways of doing that. We have here written two states, which are for the singlet and the triplet, and we can see how here we have a symmetric spatial wave function and an anti-symmetric spin wave function, and for the triplet, the other way around. There's two more of these, but I haven't written down because it's a lot of equations. But we can see here a picture where for the singlet state, there's a high probability that two electrons will come very near each other. And that makes them interact and repulse each other electrostatically. So that gives a very high energy. On the other way, the antisymmetric wave function has low probability of the electrons being together, and so there's little electrostatic propulsion. This makes a high difference in energy between those two states, and that difference is of the order of 10 to the minus 1 electron volts. And this is going to make that these states predominates, and these kinds of states are usually more prone to have spin up up or spin down down, and not up down or down up. And so this kind of interaction is going to be the most important in this presentation. Now, what is a spin wave? Well, we can relate that a bit with sound waves in a material. We know that that is just vibration of ions in our lattice that interact electrostatically. Well, it's going to be the same for spin waves. We're going to have spins that are unpaired in our material. One spin is going to start to process. We will see how. And via exchange interaction or dipole-dipole interaction, it's going to talk to other spins, and they're going to start processing all together. And so we will have a spin that travels through our material. Also, coupled to these two kinds of waves, we have some quasi-particles. For the sound waves, it's going to be a phonon, and for the spin waves, we call them magnons. And these are quasi-particles. So when you quantize these kind of waves, you call them like this. And you have some properties that you can label them with, which are energy, momentum, and spin. the spin of these quasi-particles is going to be 1, which just gives us the information that they are bosons. Yeah, that's it. Then we have two types of spin waves. One is short wavelength. This is driven by the exchange interaction. As it is very strong, it is going to be very energetic, high momentum, high velocity. On the other way, the ones that interact through dipole-dipole interaction have shorter wavelength, lower energy, lower momentum, lower speed. So less interesting for communication. And finally, in order to have this exchange interaction and have low damping in our signal, we want that the medium through which our spin wave propagates is localized electrons in a d orbital. We don't want them flowing around in a conductor, because then they scatter, they lose information of the spin, and our spin wave is gone. Now let's go to spin currents and the spin Hall effect. So in order to understand this, we need to know a bit about spin-orbit interaction Hamiltonians. And what this tells us is that somehow the spatial orbital momentum is going to be linked with the spin momentum, angular momentum. So this means that when an electron travels through a material and finds a potential, for example, made by an ion in the lattice, it's going to travel, and depending on whether it's spin up or spin down, it can scatter with different probabilities to the right or to the left. And so what we see here is that in some materials that have strong spin-orbit interaction, this is exactly what happens. And spin up travels, scatters, and has higher probability of going to the right. A spin down comes, scatters, and has higher probability of going to the left. And so we have a current that looks like this, scatters, and separates. And so we come from a charge current, and suddenly we have a spin current in the opposite direction. But here, in this axis, we don't have a charge current, because we have the same amount of electrons flowing in one way than in the other. But we have a lot of spin-ups going that way, a lot of spin-down going that way. We can also have the inverse effect, which is just that we have a spin-up coming from here, a spin-down coming from here. They meet, they scatter, but now they flow in the same direction. It's just the opposite of as in the other. So we can get from a spin current to a perpendicular charge current. Okay, now we're going to see the two effects that interest us, that are going to tell us how from a spin wave we can get to a spin current and vice versa. This first one is called spin pumping, and it means that a spin wave reaches our interface between our magnetic material and our conductor. And so the spin wave comes to the interface, it starts processing in the interface, and it's going to affect the conducting electrons that I have in my metal. And it's going to generate a spin current in that metal. And here, I'm going to have a spin current. And what have we just learned? If I have a spin current here, they're going to scatter, and if there's enough spin-orbit interaction, I'm going to have a charge current here. And I'm going to be able to measure a voltage here. Then I have the opposite. If I have a spin current that comes to my interface, these spins are going to come to interface and by exchange interaction affect a spin that is inside my magnetic material, and it's going to exert a torque, and it's going to start processing. And then I have a spin wave, because this spin talks to the next one, and so I have a spin wave traveling through my material. And so with this, we already have all the ingredients we need for our device. So what is new in this paper? What is new in this research? Well, until now, these two processes I just told you, the spin pumping and the spin transfer torque, have been tried and measured in conductors. And as I told you, in a conductor, the spin wave dissipates very quickly because it starts scattering. Okay? So these kind of materials have very low spin wave transmission. Well, the guys from this paper have chosen another kind of magnetic material, which is the JIG that I told you. It's an antiferromagnetic insulator. And so this has very low Gilbert damping coefficient, which means that we are going to have high spin wave transmission. So let's see our device, and now with all the ingredients I told you, we can understand how a signal goes from here to there, traveling by means of a spin wave. So first we come here, and we have a voltage. With this voltage attached to these two sides of a platinum plate, we're going to have a current flowing. And as we saw, this current flowing in platinum, which has very high spin orbit coupling, is going to generate a spin current. This spin current is very near the interface with this black material, which is the jig, the material, the magnetic material. So a spin wave via spin transfer torque is going to be generated in this interface. Then it's going to travel through the magnetic material, and it's going to reach the second platinum plate, which is disconnected from the other one. So we know that there is no charge transferred from here to here. And this distance is about some millimeters, so there's no tunneling or whatever. So the spin wave comes here to this interface. It generates via spin pumping spin current here, and via the inverse spin Hall effect, we get another current in the same direction as this one. And so we can measure a voltage over there. And then our signal has gone from voltage to spin wave to voltage again, but with less dissipation than if it were a normal charge current. So now let's check some of the measurements they made. First, they tried both phenomena separately. So first, we're going to check spin pumping. What they do is they induce some spin waves in our magnetic material by sending some microwaves to it. And they measure the voltage. So we can see that we have a voltage over the whole spectrum. Here we see we have a magnetic field. This magnetic field is to align some of the spins that are in our magnetic material so that we have an order system instead of spins pointing in random directions. We also see that if we increase the power of our microwave signal, we get more voltage. So we checked that indeed we have spin pumping. Then the same with spin transfer torque. Here we put a voltage on our platinum, and we see whether we have spin waves in our material or not. How do we check that? Well, it is known that as spin processes, I told you there is a damping process. So where does that energy go? Well, those spins emit microwaves too. So you can measure them. You put an antenna near the sample, and you measure how much power do you have when you augment the current that flows through your platinum. And you see that your power goes up. And they also tried that, taking out the platinum and putting some copper there, and you don't measure anything. And why is that? Because copper does not have high spin orbit coupling, so there's no spin Hall effect, no inverse spin Hall effect, no spin transfer torque, so no nothing. You need platinum or similar materials that have strong spin orbit coupling. So in the end, we come to the final results. We see our device, we put in some voltage, so some currents, and we align our magnetic field. If we put it perpendicular to our device, we measure nothing. But if we put our magnetic field along this device, then we see that in this case it's aligned parallel. We can see how for greater currents we start seeing some voltage here. And if we align it anti-parallel, so the other way around, we need a negative current, so the other way around, and we measure some voltage too. So then we are able, and we know that this device works properly. And so, what are the conclusions of this paper? Well, the author says this is a very big step in developing spintronics, because now they know that they can make a signal travel through a sample with less energy loss. And so we can base a lot of our electronic devices on these insulator-based spintronics. We also saw a device that is very useful to generate microwaves by just applying a voltage. That can be very handy. And then finally, this is more for research, that they found a very easy way of injecting a spin current into a device. Just by applying a voltage in the platinum, you get a spin current. And there's still a very long way to go. The device I just showed you, they haven't made, it's like quite big, some millimeters big. Also, they haven't measured actually
how efficient it is at carrying current through the device. So in order for these to be in our phones and computers, still a lot of things to do. So thank you very much.